We will be talking about entropy. We'll introduce entropy in this video. So, entropy is a measure of the disordered dispersal of matter or energy in a system. So spontaneity is favored by an increase in entropy. Spontaneity is favored by an increase in entropy. And we measure entropy by looking at the number of microstates our system or the particles within our system form. What we mean by microstates is basically particles are dynamic, right? They aren't static unless we are at absolute zero, right? But for the most part, in most of the conditions that we will talk about, unless it's specified that it's at 0 Kelvin at 0 Kelvin, the particles can move, they're dynamic, right? So the microstates is all of these configurations of the particles, right? It takes into account the locations and energies of the particles in our system. And this is how we measure entropy. We measure entropy by taking into account all of the microstates the particles within our system form. So we measure spontaneity by using the formula for entropy, which is S, which is entropy, is equal to K natural log of W. K is the Boltzmann constant, which is 1.38 times 10 to the negative 23 joules per Kelvin. W is the number of microstates possible for the particles within our system. So, pause this video, and while keeping the Boltzmann constant, no pun intended, plug in different numbers for W. And what do you notice mathematically, right? So you can plug in any number for W while putting in Boltzmann constant for K, and then calculate entropy S and see what you notice mathematically. You're going to do this directly into your lecture worksheet. Pause me and come back. All right, welcome back. So here is what you may have noticed when you plugged in these different values for W. The more microstates, right, basically the freer the particles are. The more microstates the particles form, the freer they are. The more spontaneous they yearn to be, the more disorder they cause, the higher the entropy. So essentially, as you increase the value of W, or the number of microstates, you saw that entropy also increases. An important relationship to understand. So the number of microstates possible is really a measure of particle freedom, right? And it's given by W equals n to the nth power. N is the number of boxes, right, that the particles can move between. And capital N is the number of particles in our system. So let's do another scenario where you're going to solve for W for the following two scenarios. So for 1A and 1B, you're basically keeping the number of boxes constant, and you're changing the number of particles, and you're going to see what W equals in both of those scenarios. For 2A and 2B, you're going to keep the number of particles constant and change the number of boxes that they can occupy, and then calculate W for both of those scenarios. And then you're going to look at how much W changes between 1A and 1B, and then 2A and 2B. And I want you to draw a conclusion about what that means, right, based on your values. So again, pause this video, do these calculations in the worksheet. Welcome back. So I am showing here what I calculated for the ratio of W, right? So I did this calculation for 1A and 1B, and I basically see that W increases by a factor of 4 when I keep the number of boxes constant and I change the number of particles from 10 to 2. In the second set of scenarios, right, where I keep the number of particles the same and change the number of boxes that they can occupy, W also increases by only by a factor of 1.44. So it seems that changes in the number of particles affect the number of microstates more dramatically than similar changes in the number of boxes. So just breathe that in, reflect on that a little bit more. Hint, hint. I don't know what it's a hint for, but reflect more on that. Look at your calculations, compare, see if your calculations also come to the same conclusion. All right, and I'll see you in the next video.